So 8, and then I invert color, and then Control C, and then Control V. So it look better, right?
So actually the current value of the current is like 40.72. So I didn't use the 2, and that's why like there's this error of like slightly less than 2.4.
Next time you should invert the color.
Okay.
Like this. Okay. Just put in the content. Don't put everything. The thing, right? You only put the graph and the acid and dry acid, right?
Okay.
Like that in the paper, right? Like this. Okay. Actually, you can scale it by doing this way. You can scale like this. Okay. You scale the So if you want to screen maybe in your like square like this. So
then I just scale. Okay.
So you should scale your graph like square and then cut, right? So the graph will look nice. And let's see. So in here, about 22, but in your simulation is only under 20.
Yeah, I know the result. Yeah, the results are actually slightly different.
I think it is big different, right? It's not slightly.
Yes. Not slightly, yeah, it's a big difference.
Here will be 18, right?
18, not 18
22.
actually. Yeah, but it will be lesser than 20, yes.
18 and 22. For it is 18%. It's not small. So we will say small when it under 10%, right? It's around 20% different. So when you see a big difference over 10%, you should think why, right?
So my assumption is that the diodes are working differently in the simulation.
So next time you should include the equation here. So we cannot look only graph, right? We have to look equation too. So you should put this here. So we can see and compare, right? We can find y. So what is your assumption? Diode?
Yeah, I think that like diode VD, like that's the difference.
In here, right? Vref SO max.
Yeah, the Prect max, in the Prect max there is VD there. So like because of the VD, difference in paper and in the simulation. In the paper, the VD value is 0.38 volts.
So let's do one calculation here. Your max is 18, right? 18. 18 so and CP.
So 2 times 12 into 9.
Let's calculate what a VD in the simulation. So it is 18.
So the Prect is 18, right?
By
18 into
divide CP is how much? 12 nano.
0.57. The
Oh.
VD in the simulation is 0.57.
Zero, how much?
0.57.
Yeah, 0.5. 0.5. So let's check. Actually,
So almost 0.6 actually.
I make a new test band here to check VD. Here is a diode. Diode here, so I put this is VDC, so a DC voltage in analog library. Did you look at the library yet?
No.
Here is in analog library. We will have many values. So again, in analog library, you will have VDC, DC voltage, and we will use VRC, no, V shines, right? We will have for sine wave and for pulse and for making pulse. And I also have seen, right, for current, for PAT current, right? So, and inductor also. So it is on in this library. You can look later.
Okay.
So here we VDC, I call it DD, and then here is ground, and then I will save the voltage, the current in this node to see the current flow to the diode, right? ID is M4. This is M4S. Okay, and then I run switch from VD from minus 0.1 to 1 volt, and then let's check.
ID value is constant.
So with different values of VD, right? In here, you will see many graphs. So if you want to make graph like in this simulation, P power actually is a single value, right? It's single value. So when you finish your sweat simulation, it will automatically graph like this. However, in here, it is transient. So it is a graph, right? Right? It is graph, it's not a value. So we should see only one value. It's on more constant. Maybe in the beginning, it's maybe slightly different, but almost constant. So we only want to see one value. For example, 100 millisecond, and then we right click here in time, right? Right click time and then swap, switch, and then you put the time you want to see the values of PD. In here is 100 millisecond. Okay, and then it will plot. So it plot all the values in 100 millisecond to here, right?
Yes.
So then you can see VD. Actually, it should not 600.
If you will zoom, then it will
You
be like 0.3.
in your circuit only about 40 microampere flow, right?
Mhm.
So here you can see I read. Let's see. It's only flow 40 microampere, right? 40 microampere. 40 microampere is around here. Only 330 millivolt. It's not 600 millivolt, right? Like you calculate.
But like if I calculate the if I use the maximum power equation, then it's saying it's like 0.57.
Yeah, it is calculation, but I want to check in simulation.
Or is it like because like the theoretical and like simulation difference?
No, it a bit different, too big, so you have to think.
Mm-hmm. Why? Okay.
So let's see. Here you can check. You can see the plot here, right? VSO. The maximum is Vref plus 2 VD, right?
Mm-hmm.
Now let's check. Where is VSO?
I think it will have a different notation.
If you delete it,
No,
Uh,
I didn't do it.
VPN switch only. So it's here. 1.9. And VR is 1.2, 1.9, 1.9, 1.9 minus 1.2 divided by 2. Yeah, it is only VD is only 0.3 volt, right?
0.3.
Right? Is it correct?
Yeah.
So this means your assumption here is wrong.
I see.
Not because of VD.
But like then why?
Let's see. Let me check the current output current.
There can be actually another reason.
But
Let me think about it.
maybe because of this week, maybe
This one?
the sweet
Mm-hmm.
this week.
But like it's happening in all three, like even in the full bridge rectifier, the results are different.
So it's all reduced.
Even in the full bridge rectifier, the results are different from the paper.
I mean, on your simulated result is decrease compared to paper.
The full bridge, go to the full bridge rectifier.
So here you have maybe 15, right? For 10 micro. In here around 20.
I mean, here you can see like for except the 820 in my simulated result, except for 820, we have flat lines, but here there's no flat line. So
Here, flat here.
yeah.
Yes, actually because
Yes.
because the power reduced, and so it's like the graph is being reduced, right? This will reduce all the things, and then you here you voltage to get the power values also reduced. And here 22 micro and 10 micro is big difference, but for your case 22 is close to 47, right? In here in your paper 22 micro and 47 micro is big difference, but for your simulation is almost similar. So let's check your output current first. Output current of IPAT, PGPU. Current is not big difference. I think to save our time, I think it should be your homework, right? Now in our meeting, we should not try to solve problem in our meeting. So in here, your issue is why power from uh, from transmit only 20% smaller than paper. Okay. and then in here y22 micro and 47 micro is look similar. And in here different materials by flip. And why? Okay. Hello? Are you here? Right.
So I got it understood.
Did you got it?
Yeah.
So you should check your waveform again. Right. It's a waveform of current and voltage. It have voltage and current. You should check again, and you might change the size of your switch, right? In here, you have your switch size, and then you might change the switch size and other things, change the values, and you can change your power width of your switch. So the power width here. So the time the switch will turn on and turn off, you can change it through here. Here I set 10 microsecond, but you can change it and check, right? You should figure out why it's big difference. Okay, got it? Do you have question? Hello? Hello? Do you hear me?
Yes.
Ryan? Hello, Ryan? Hello? Where is Ryan? Hello? Hello, Ryan? Can you hear me? Hello? What's wrong? Do you hear each other?
Yeah, I still can hear.
Ryan, are you here? Hello, Ryan? Why is turned on my why? Ryan, Ryan chạy đâu rồi nhỉ? Anh em có nghe Ryan nói không?
Không, không nghe được cái gì cả.
Không nghe Ryan nói á?
Không nghe được.
Hôm nay mình chạy đâu rồi nhỉ? Em tự nhiên chạy đi đái rồi. Tự nhiên đang nghe nó nói mà đúng không? Tự nhiên nó chạy đi đâu? Thái, em xem simulation chưa?
Em đang đọc cái trước với tập mô phỏng lại này.
Nhưng mà em đã mở cái file mô phỏng hay gửi chưa?
Rồi,
Hả?
rồi, nhưng mà em chia sẻ.
Chưa chạy được á? À sao?
Vâng. Thì em chưa chạy em mới xem cái sơ đồ rồi. Thì em đang đọc cái
Tức là
trước
em
cái
mở được cái file simulation rồi đúng không?
Vâng.
Ok.
Có gì tuần sau anh tổng hợp lại rồi em báo cáo một lúc.
Ờ.
Vâng.
Mở xem lại video rồi check lại nhá.
Vâng.
Về xem lại simulation hôm nay luôn nhá.
Dạ.
Rồi em chạy đi đâu? Chạy được. Hoàng có ý kiến gì không? Sao tự nhiên thấy
Đấy bình thường.
power khác hơi nhiều đúng không? 20% mà. 20% mà.
Ừ, nó hơi khó ấy, kiểu mình phải mô phỏng mình mới biết được ấy. Chứ còn ngồi nhìn này hơi khó nói.
Đấy, thì kiểu mình check từng cái, check hết waveform các thứ. Tất nhiên đây em chạy vào nhé. Thế nên là mới làm lúc sáng, mới hỏi lúc sáng. Làm được. Được. Đó, thanh niên chạy đâu rồi nhỉ? Thầy nói đang gì đi. Hay là bấm máy gọi nó. Anh tự gọi xem nhé. Sao tự nhiên cho nó tôi làm chạy.
Actually, the meeting is almost over, so did you rejoin?
Hello? Where did you
Hello?
go?
I'm here. Actually, the meeting is almost over. Like, should we rejoin?
What?
The meeting is all like what 4 minutes left only.
It's over. You mean? However, where did you go? You have
I
gone.
was actually here. Like, I maybe wait for a washroom or something, so I didn't notice. Sorry.
Why we could not hear you for a while?
Oh, sorry. Actually, I sorry. So, what did you say?
So did you got the question?
Oh, question no, actually, like question no. So the next time I should like think why this switch, why the power difference. That's it.
Yeah, you should check again to answer why first. Why in here in switch only rectifier your power is about 20% different, right? In here you only have around 18 microwatt, but in your paper is 22, so it is about 20% different. Okay.
Okay. Okay.
So you should check again on the waveform of the circuit only, whether it's on correct,
Mhm.
and then find out the reason why. Okay.
Okay. Okay.
The second question is in the bias flip in
Yeah,
here,
two graphs are almost similar. Yes.
right? It should be different, right?
Yes. Yes. Yes.
But in here is similar. So why? You should be
Okay,
able to answer this question.
Okay, I will try.
Okay, let's try and other thing is I will tell you how to make like a
This
symbol.
schematic in.
Symbol here on the schematic have the similar PJT, right?
Mhm.
Similar PJT, so you can make a new symbol for it. So let's do like this. I will close this without that and close it. Do you know we can copy the schematic from this one library to another library? Like here. Here is the library I'm working on, right? I can copy it. Copy. Here is from my library into your Ryan library. Okay. Okay. Okay.
see.
So your diode set band is already in your. And then I
So
want to make a symbol for your PAT. So I will go. First, I will copy this headband and then I hear the PAT. Okay.
Hung, are you saying something? I can't hear you.
Yeah. In here, first I will copy it. I will copy this headband first. Okay. I rename. I will do in my library. I will first copy this headband, and then I change to PJT model. Okay. Okay. We have PJT model here. PJT model. Delete all. PJT model. So you will create some pin. Add pin and then input output. In here we have VP high, and then here VP here. Actually we can add pin by typing P in the keyboard. Type P. Okay. VN. We have VP and VN. Shift H to save, and then create cell view from cell view. Okay. And then click OK. So in here, you will have two pins, BP and VN, right? BP and VN. You click OK. You will have a symbol like this. symbol like this. Let's move. Yes. So in the schematic, it will have current, capacitor, and resistor. So normally I will draw the similar. First, let delete this. I will draw a similar symbol. So we'll have current. Take here. This plus. Remove. Current, and then you draw capacitor. And then draw resistor. Okay, you draw it, and then you move the pin. Go to here, VP. And then yeah, okay. Okay, save it. Okay. And then here you add instant. You type I in the keyboard, I at instant brown. Now you have PV model, PIT model here, click symbol. Okay. Now you have a symbol. Instead of this, now you have symbol, and then okay. So you have similar things, or you can make your circuit look simple. Actually, now your test band is small, but when your circuit become bigger and bigger, you should make your symbol like this. Did you got it? Okay. So in here, it's when you save, it will say warning. Warning. You can check here. Warning because floating BPJT open circuit. Because if this node is floating, it's called warning. So you should go here, go to library, basic library, and go to no connection. You add no connection here because it's floating. So you should add no connection. So then warnings disappear. Okay. When you have a floating node, you will add this one to remove your warning. Got it?
All right.
Okay. Anything else? Do you have any question in schematic and simulation?
No.
Okay. So yeah, I think that is for the day. So I during this simulation, I might have some other tips, but I cannot remember now. So before I send you this note I made, so before when I was start learning cadence, I take notes on the things like the script analysis, right? I told you script analysis. I also take notes it and how to using calculator. I think you guys also need to make your own notes because now you remember, but later you might forget. So you have to look back. So if you
Well,
think something difficult,
did you
yeah,
send this note before?
I send you in your
I think the meeting 3, right? Yeah.
meeting 3, right? This setup in here. So you, if you have time, you can have a look.
Okay.
Later, later I will train you guys about layout and other things, and then you can have a look here first, layout, and in here is in BCD process. Actually, my first work is not using BCD process, but the IF process. IF process here, TSMC 18 IF process. So from A, B, and then 6, 7, 8, 9. Except TSMC BCD, the red is for IF process. So it's my different from the BCD process you are looking at, right? Okay. Later I will tell you when some issues come, and I think that is for today.
So
Okay.
for the next day, we should just like think about like the power difference tested, right?
Yeah, check it, and then if you finish it soon, let's continue to review this paper.
Okay. So
in here in
I finished that bias rectifier after bias rectifier.
DC-DC buck converter.
Yeah, I didn't review that
Yeah.
part.
So after rectifier, I will let you guys how to simulate a DC-DC buck converter. Okay?
Okay.
DC-DC buck converter review. Actually, our purpose is for triboelectric, but triboelectric is more advanced compared to PJT. So I think it is better for you guys to learn your basic first. So I will let you guys learn your circuit for PJT first, and then if we have time, I will train you guys the PJT later. The triboelectric later, because it will need to cope with the high voltage and high voltage devices. Now it's easy complex for you guys, so we should learn the basic first. Okay, got it?
Okay.
Yeah.
Okay, thank you. See you next week.
Thank you.
Bye.
Thank you.